In section 3, we're going to talk about horizontal and slant asymptotes. So we're going to start with definitions. A horizontal asymptote is a horizontal line. The function approaches as x goes to either positive or negative infinity. So it's got a very similar definition to a vertical asymptote, except instead of a vertical line, it's a horizontal line. An oblique asymptote, sometimes referred to as a slant asymptote, is a linear equation. So it's of the form y equals mx plus b the function approaches as x goes to, and again, positive or negative infinity. So again, these are both going to deal with horizontal lines in the form of y equals, and then we're going to talk about in a little bit specifically how you know which one a graph is going to have. But first, let's go ahead and talk about how to identify these from a graph. So looking at a graph, in order to identify a horizontal asymptote, you're looking for a y value the graph is going to approach but never cross. And looking at our first example here, the graph is approaching the y value of 2, but is not actually crossing that value. So that would be my horizontal asymptote. So y equals 2. Oblique asymptotes are sometimes a little bit harder to identify. So in the second graph, it would have an oblique asymptote. There's a horizontal line that kind of goes right through the middle of these two graphs. It's equidistant from each part, and that's going to be my slant asymptote. So, and this is just going to be an estimation. It appears to be the equation is y equals negative x plus 5. And again, this is just an estimation. That may not be the equation. I'm just guessing based on the graph. If you know the function, you can identify the exact oblique asymptote, but it appears to be roughly about y equals negative x plus 5. So let's go ahead and talk about how to find a horizontal or oblique asymptote. And we're going to be able to do this from the equation of the function. So we have to identify between proper rational functions and then improper rational functions. So a proper rational function is a ratio of polynomials, which is the definition of a rational function, in which the degree of the numerator is less than the degree of the denominator. And when this happens, we always get a horizontal asymptote of y equals 0. So anytime you're given a rational function where the degree of the numerator is less than the degree of the denominator, you're always going to have a horizontal asymptote, and it's always going to be the horizontal asymptote of y equals 0. So now we want to talk about how to find horizontal and oblique asymptotes of improper rational functions. So this is actually going to be two different cases of asymptotes. So an improper rational function is a ratio of polynomials, so a rational function, in which the degree of the numerator is either equal to or greater than the degree of the denominator. So we have to talk about each case. So when the degrees are equal, when that happens, we have a horizontal asymptote of y equals a over b, where a and b are the leading coefficients of the polynomials. So if the degrees of your rational function and the numerator and denominator are the same, you just divide the leading coefficients to get your horizontal asymptote. So it's still y equals. When the degree of the numerator is greater, this would be when we get a oblique asymptote. And it's found by using long division. So there is no other way to find the oblique asymptote other than to use long division with our two polynomials, and it's going to be the quotient without the remainder. So it's whatever the quotient is when you divide your two polynomials. So to kind of recap, when you have equal degrees for your rational function, you divide the leading coefficients, and if the degree of the numerator is greater, you always use long division to find the oblique asymptote. So it would be the case where you get some function of the form y equals mx plus b. So let's go ahead and do some examples. So we have f of x equals negative x squared plus 1 over x squared minus 5x plus 6. And we just want to do horizontal asymptotes. So first thing we want to do is identify the degrees of our numerator and our denominator. So my numerator is degree 2, as is my denominator. So when the degrees are the same, it's a horizontal asymptote, which I'm going to abbreviate HA. And to find it, we divide the leading coefficient. So y equals, the leading coefficient in my numerator is negative 1. The denominator has the leading coefficient of 1. So it's negative 1 over 1, which is just going to simplify to negative 1. So if I were to graph this rational function, I would see that it's never going to cross through the y value of negative 1. The ends of my graph are going to come close to it, but it's never going to cross through that y value. Our second example is h of x equals 16x cubed plus 2x plus 8 over x squared plus 2x plus 1. So identifying the degrees, so the degree in my numerator is 3, the degree in my denominator is 2. So this is the case of the numerator being greater than the denominator. So this is going to be an oblique asymptote, which means we're going to have to do long division. So when we set up long division, the polynomial in the denominator is going to go outside, so x squared plus 2x plus 1. And underneath, we're going to have 16x cubed plus 2x plus 8. So now we need to do the long division. So I start by taking 16x cubed and dividing it by x squared, and we're going to get 16x. Now I need to multiply 16x by what we're dividing by, x squared plus 2x plus 1, which is going to give us 16x cubed plus 32x squared plus 16x. So we're going to go ahead and put it in parentheses, 16x cubed plus 32x squared plus 16x. And with long division, we're always subtracting. So I always put it in parentheses with the subtraction out front, and then I do the subtraction. So I have 16x cubed minus 16x cubed. Those first terms should always cancel. And then if I look, my next term is an x squared. Well, my original polynomial does not have an x squared term. So I'm doing 0 minus 32x squared. So I'm going to end up with a negative 32x squared. And then I have 2x minus 16x, which is going to give us negative 14x. And then there's nothing with the 8 to combine with, so we're going to bring down the 8. Okay. Now we need to do negative 32x squared divided by x squared, which is going to give us negative 32. And just like our first step, we're going to multiply it by what we're dividing by. So negative 32 times x squared plus 2x plus 1. So we distribute the negative 32, we get negative 32 x squared minus 64x minus 32. Go ahead and put it in parentheses underneath in my long division. And we are subtracting. So negative 32x squared minus a negative 32x squared is going to cancel. Now when I do negative 14x minus a negative 64x, it does change to addition. So I'm doing negative 14 plus 64, which is going to give us 50x. And then I'm doing 8 minus a negative 32, which just change it to addition, and 8 plus 32 is 40. So I end up with 50x plus 40. And this would actually be our remainder because I can't take 50x and divide it by x squared. So we're done with our long division, and our oblique asymptote is going to be our quotient that we have. So my oblique asymptote is going to be y equals 16x minus 32. And that is the oblique asymptote of our function. In our last example, we're going to go ahead and combine what we learned in section 2 with what we're doing in section 3. So we want to find all of the asymptotes, vertical and horizontal, in the rational function. And the horizontal could mean an oblique asymptote. So in order to find a vertical asymptote, we first have to factor our function. So if we look at our numerator, There is a GCF I can factor out of 2x squared minus 8. So I'm going to factor out the 2, end up with x squared minus 4. And our denominator, x squared minus 8x plus 7, is going to factor as x minus 7, x minus 1. So to make sure that there aren't any holes in our function, we do have to finish factoring our numerator. So x squared minus 4 is a difference of squares. It factors as x minus 2, x plus 2. And our denominator is still x minus 7, x minus 1. If we look, there are no common factors that appear in our numerator and denominator cancel. So we're not going to have any holes. So we do have two vertical asymptotes. We have vertical asymptotes, and they're going to be at what makes our each set of parentheses 0. So they're going to be at x equals 7 and x equals 1. Next, we want to identify a horizontal asymptote. And if we look back to our original function, the degree of our numerator is 2, and the degree of our denominator is also 2. So they're the same. So it is a horizontal asymptote. And because the degrees are the same, we're going to divide the leading coefficients of our numerator and denominator. So it's going to be 2 divided by 1, so it's going to be a horizontal asymptote at y equals 2. And if you do graph this in Desmos, you won't actually be able to see the equations of the vertical and horizontal asymptotes, but when you graph it, you should be able to identify that at these x values and this y value, the graph does approach that line without actually crossing it.